In this video, we continue our discussion of linear algebra concepts. I should mention that the way we're doing this is not so much to be mathematically precise, but do this in kind of an intuitive way so you get kind of a geometric understanding for these linear algebra concepts. So the next concept we look at is that of linear independence. A set of vectors v1, v2, and so on through vn is called linearly independent if the only way the linear combination x1 v1 plus x2 v2 and so on plus xn vn is equal to 0 is if each coefficient x1, x2, x3 to xn is 0. Let's see what this means geometrically. So we look at two vectors in the plane. These two vectors are linearly independent because there is no way of combining them to produce 0 except by multiplying both of them by 0. On the other hand, these two collinear vectors can be combined to produce 0 by just scaling one and doing the negative of the other. Similarly, three vectors in 2D can be combined using non-zero coefficients to produce 0. So those are linearly dependent. The next concept is span. The span of a set of vectors v1, v2 to vn is the space obtained by forming all possible linear combinations x1 v1 plus x2 v2 and so on xn vn. So for example, the column space of a matrix A is the span of the columns of A. The next concept is basis for vector space, a very important idea. So if a set of vectors v1, v2, vn in a vector space is linearly independent, so first this set of vectors is linearly independent, and the span of this set is the entire vector space, which means that by linearly combining these vectors, we can produce every other vector in the vector space. Then such a set is a basis for the vector space. We say a basis and not the basis because a basis is not unique. We'll see this with this example. So what's the basis for R3? The most obvious basis is the collection of 0, 1, 0, 0, 0, 1, 0, and 0, 0, 1. Let's take another collection of three vectors and ask if this is a basis. To test if this is a basis, you take a matrix whose columns are these vectors and ask if that matrix is non-singular. Ask yourself, why does the non-singularity of this matrix mean that this is a basis? And second, how do you check the non-singularity of this matrix? With MATLAB as a tool, there are a number of things you can explore. The next concept is the dimension of a vector space. The dimension of a vector space is the number of elements in a basis. The next idea is the null space of a matrix, which we denote scripty n of A. This is the space of all inputs for which the output is 0. So it's the set of all vectors which, if we multiply by A, results in 0. Let's look at an example. Let's take this matrix A, 1, 2, 3, 4, 7, 10. So A takes R3 to R2. We understand what that means now. Is there a vector x star such that A times x star is equal to 0? Just by inspection, we can figure out that A times 1, 2 minus 1 is 0. So if we take the line that contains 1, 2 minus 1, that entire line is the null space of A because that entire line is mapped to 0. Okay, think about this, understand what that means. Let's take another example. This is the A matrix from the previous video. We'll use this matrix a lot in the coming videos as well. So by inspection, we can construct a basis for the null space of this matrix. One such basis is minus 1, 1, 0, 0, and minus 2, 0, minus 3, 1. You can check that these two vectors are linearly independent, and A times each of them is 0. So how do we find a basis systematically, not by just by inspection? One way is to use reduced row echelon form, which you're probably familiar with some undergraduate linear algebra that you did when solving linear equations by Gauss elimination. You can see how the reduced row echelon form constructed in MATLAB by the function ref leads to that basis. A better way to construct a basis for the null space of a matrix in MATLAB is using the function null. So null of A returns null space of a basis for the null space of A. These two functions give different answers, so you can think about why. Finally, the concept of rank of a matrix is the dimension of the column space of the matrix. In MATLAB, we can use the function rank of A.